So let's implement this end-to-end emotion detector. We will be using a fantastic dataset about how emotions are conveyed in English Twitter messages to create our emotion detector. This particular dataset includes 6 fundamental emotions, which are as follows: anger, contempt, fear, joy, sadness, and surprise. Our goal is to train a model that can categorize a tweet into one of these moods or emotions given the input tweet or input text. The first step is we have to install libraries. So the first step is library installation. Primarily, we will require these two libraries. First is transformers and second is datasets. So let's install these two libraries. It will take its own sweet time to download and install these transformers and dataset libraries. Now, here we can see that both the libraries are successfully installed. Now, let me give you a brief about Hugging Face datasets. The data will be downloaded from Hugging Face Hub using Hugging Face datasets. Now we have something called as list datasets. From datasets import list datasets. Now this list dataset method can be used to determine what all datasets are available on the Hugging Face Hub. So I'll take the variable all underscore datasets, which equals to list underscore datasets. Again, it is taking its own sweet time. Now let's print how many datasets are available. So let's type total datasets available length of this all datasets. That's it. So Hugging Face Hub contains about 32,610 datasets. Now if you want to print the name of these datasets, we can simply print all underscore datasets. Now it will print all these 32,610 datasets. So we have something called as XM, we have submission scores, we have fake news data, we have Quora, SWE, and so on. So you can use any datasets out of this 32,000 list. Okay. In this tutorial, we will be using emotions dataset. So here I'll write emotions equal to load underscore dataset. So load dataset is a functionality which we have to import again from datasets package. From datasets import load underscore dataset. Now we want to import the dataset of emotion. Now this emotion dataset first will be downloaded and then will be stored in emotions dataset. Now here you can see that the dataset is downloading. Here we can see the dataset is successfully downloaded. Now let's explore this data. So data exploration. of emotion dataset. Okay. Now, a thing to note that this Hugging Face datasets is based on Apache Arrow, which defines a typed columnar format that is more memory efficient than naive Python. Let's print this simply emotions variable. So this emotion variable is nothing but this one. So let's see what is there in this emotions variable. Here we can see that there are three main keys. First is train, second is validation, and third is test. The train dataset consists of about 16,000 number of rows or number of instances, and each instance has two features, that is text and label. Label is a target attribute and text is the text or the sentence. Similarly, with respect to validation, validation has 2000 rows or 2000 instances containing text and label. Similarly with test data is about 2000 number of rows. Now let's focus on train data. So I'll take another variable which is called as train data, and I'll take this emotions of train. Okay, and I will simply print this train data. Now here we can see that by printing only train data, we have number of rows to be 16,000. Now what is exactly there in the 60,000 we don't know, but there is something 16,000 text instances in this training data. Now let's print the top 5 instances out of this 16,000 training instances. In order to do that, we will simply use train data of 0 to 5. Here we can see that the text is I didn't feel humiliated, and the label which is attributed to this particular text is 0. This 0. Again here we can see that this is the second train instance, and the label again it is attributed 0. So in this way we can print out the first 5 instances from the training data. Now suppose if I just want to print the text from the train data, so we will simply write train data of text and 0 to 5. So it will just print the text, the first 5 text out of 16,000 text. Suppose if I want to print only label, so train underscore data of label 0 to 5, or I can simply type as this one up till 5. So here it will print the first 5 labels. Now what this 0, 3, 2, 3 means, we don't know it yet, but we can find out by using something called as features. So this train data variable has an attribute named features. If we print this, we have something called as names. Okay, in this we have text and we have label. In this label we have names, and in these names we have all these emotions. So first emotion is sadness, then joy, then love, then anger, then fear and surprise. So 0 stands for sadness, 1 stands for joy, 2 stands for love, 3 stands for anger, 4 stands for fear, and 5th stands for surprise. So total there are 6 emotions. Now let's convert this Hugging Face dataset into a more manageable data format in Pandas. So let's convert Hugging Face datasets to Pandas Dataframe. Now this is because we want to go in depth or to explore in depth about this particular data. For this we obviously want to import Pandas. So import Pandas as PD, and then in order to convert this emotions dataset to Pandas data frame, there is something called a set format functionality or set format method. So emotions dot set underscore format, and we have to write here type equal to Pandas. That's it. But this Pandas has to be encoded in single quote or double quotes. That's it. We have converted this emotions from Hugging Face datasets to a Pandas data frame. Now we can print the type of variable, this one. So here after printing type, it will print as datasets. Okay. Now let's consider a variable which is called as train underscore df. So train data frame, and assign it to be the training data. So emotions of train. Okay. And I want all the rows. So that's why this one. Okay. So now let it run. Okay. So if I print head or first 5 instances, it will show me in tabular format. So first column is text and second column is label. Now you all know that what exactly this 0 stands for, 3 stands for, 2 stands for. As you can see, the first few rows correspond to how we previously viewed the data, and column headers have been kept. But because the labels are integers, that is 0, 3, 1, 2 and so on, let's utilize int2str function of the label feature to add a new column to our data frame that contains the names of the relevant labels. So here we can use label integer to string method, and we will pass into row. So emotion underscore label equal to emotions of train dot features, and we have something called as label features of label dot into str. This is the inbuilt functionality of features, and insert and in that we will pass this row and return emotion underscore label. Let's run this. So we have created this function, we have defined this function here. Let's apply to our train data frame this. So train data frame, we will create a new column which is called as label name, label underscore name equals train underscore df of label, and we will apply this entire functionality of label int to str. Okay, let's run this part of code. Oh, there is something, this one. Okay, now we have this train data frame. Again, let's print head. Here we can see that we have third column corresponding to the actual emotion in text. So here 0 standing for sadness, and 3 standing for anger, 2 stands for love, 3 stands for anger, and so on. Let's explore this data more. So let's explore this data more exploration. Okay. Now it is a good idea to look at the distribution of examples throughout the classes whenever you are working on text classification tasks. In terms of training loss and evaluation metrics, a dataset with a skewed class distribution might need a different approach than the one with a balanced distribution. So in order for data visualization etc., we will use matplotlib. So let's import matplotlib library. matplotlib.pyplot as plt. Okay. Now we have this train df, we have this label name. Okay, we have this label name here. let's print how many instances of sadness are there, how many instances of anger are there. So value underscore counts, and we will set here ascending equal to true. So this will tell us whether our dataset is balanced or not. So here we can see that the dataset is obviously not balanced because the instances of joy are more than that of others. So instances of joy are about 5,000 and surprise is only 500. So there is a lot of imbalancedness in this type of data. Now let's plot this up to visualize it more. So this train DF of label name dot value counts, again we will write ascending equal to true. Now we want to plot it. So dot plot dot bar chart horizontal. We will set the title to be class or label or target distribution, and then we will show this particular plot. So in order to show it, plt dot show. Okay, let's see how our plot looks like. There is something. Okay, so here I have made a spelling mistake. It should be counts. Now let's see how the bar chart looks like. So here we can actually visualize that the total number of instances of joy in the training data are more than that of surprise. So this is an imbalanced data set. Okay. Now there are different techniques to deal with imbalanceness. The first technique is randomly oversample the minority class. The second technique is randomly undersample the majority class. And the third sample is gathering more labeled data or more annotated data from the underrepresented classes. Now, but in this tutorial, we will work with imbalanced raw frequencies to keep the thing straightforward. We will not deal with this data imbalance, which is out of scope of this particular topic, which we are studying today. So I strongly suggest you all reading the imbalanced learn library or IMB learn library if you want to find out more about the sampling methods. These sampling methods are used to deal with this data imbalance problem. A note here I want to tell you all is that just be careful not to use the same methods twice before setting up your train or test device, or there will be a lot of data leakage between them. So here data leakage means that the number of samples which you are using in the train data, they might be replicated in your test data. So just make sure of this. Let's dig more into the data. Now here we will analyze the distribution of words per tweet or per text. For this we can derive an approximate idea of the lengths of tweets of each emotion. So train underscore df, let's take another column, that is tokens per tweet. Okay, tokens per tweet equal to train df of text dot str dot split, and we will apply the length functionality. Okay, and we will print head or the first 5 rows. Here we can see that another column is added, that is token per tweet, and it has some integer numbers, or it's a simple number. So here 4 represents that the text or the tweet contains 4 words. 21 means this text has 21 words, and so on. Now let's print, or let's plot a box plot. So train df dot box plot, and I want to this box plot is for tokens per tweet. Okay, and by label name. So I'll show this. So there is something called as key error. I think this is label underscore name. Okay, so according to this plot, we can see that average length for each tweet. Okay, here this green line is the average length for each tweet for each of the classes. So for anger, for fear, for joy, for love, for sadness, and for surprise, we can see that the average tweet is hovering around 15 to 20. So we can take it as, let's say, 16 or 17. This is the average length of a tweet. So the average length of tweet for each and every emotion is 16 to 17 words. Okay, and these are few outliers which has very high number of words in a tweet. So this particular box shows that this joy tweet contains 60 words. Okay, now the algorithm that we will be using, let's say BERT or BERT, has something called as maximum context size or maximum sequence length. Now text that are longer than a model's context size, they are truncated, okay, or they have to be shortened. However, if we shorten a text, we might lose some information and performance might suffer, right? Let's now determine how to transform this unformatted text into one that Hugging Face transformer can use. Since we no longer require the data frame format, let's also reset our datasets output format while we are at it. So let's reset the dataset format. Okay, so in order to reset the dataset format, right back to Hugging Face, we will use reset underscore format. Again, let's print type of this emotions dataset. So here we can say that now it is of the format datasets. Earlier it was a format Hugging Face. Earlier it was a format Pandas data frame when we converted it into Pandas data frame. Now we have got the original datasets format. Now let's convert this text to tokens. So let's perform tokenization. So converting text to tokens, or we call it as tokenization. Okay. Now transformer models like BERT or BERT expect that the text has been tokenized and encoded as numerical vectors and cannot accept raw strings as input. Tokenization is a process of dividing a string into model's atomic components. One can use a variety of tokenization techniques, and the best way to break down words into their component parts is typically determined by studying a corpus. Now let's jump into subword tokenization, which BERT, BERT or encoder based transformer uses. Now subword tokenization's fundamental goal is to combine the best elements of character and word tokenization. On one hand, we want to break the uncommon terms into smaller chunks so that model can handle complex words and typos, but on the other hand, we want to preserve common terms as distinct entities so that we may control the length of our outputs or inputs. Now subword tokenization, it's just like word tokenization, is primarily distinguished by the fact that both are learned from the pre-training corpus using a combination of statistical principles and algorithms. The BERT and DistilBERT tokenizer use wordpiece, which is the first of numerous subword tokenization algorithms that are frequently used in NLP tasks. Now let's see this wordpiece subword tokenization in action. We can use from transformer import auto tokenizer. We will provide the model name to be DistilBERT base uncased, and we will have this tokenizer to be auto tokenizer. We will import this tokenizer. So tokenizer dot from pre-trained, and then we will pass the model name to it. Model name. If this is your first time, it will download this tokenizer of this model name. I think I have made a typo mistake. Yeah, transformers. Okay, see here it is downloading the vocabulary and tokenizer. So this auto means a broader group of auto classes including the auto tokenizer class. Now this is responsible for automatically retrieving the model's configuration, pre-trained models, weights or vocabulary from the checkpoint name. This enables easy switching between models, though you can also manually load the desired class if you like. Okay. So let's take up a text example. So text is, let's say, hello, I am an example of text classification. Okay. Let's tokenize this sample text. So tokenized text equal to, we will call this tokenizer variable and pass in the text, and we will print the tokenized text variable. So here we can see that all the words from this, they are now converted to distinct integers. These integers, just like character level tokenizer. Now the function of the attention mask, this one attention mask, I'll discuss in the next sessions. Okay, for now just focus on this input IDs. Now we can use the tokenizers convert IDs to tokens method to turn the input back to the tokens. So if we want the original sentence back from this, we can simply use the following code. So tokens equal to tokenizer dot convert underscore IDs to tokens, and then we will pass this tokenized text and tokenized text of input IDs. So we will pass input IDs of this tokenized text. Okay, and we will print these tokens. Now here you can see that we have regenerated the original tokens from input IDs or from these distinct integers. Now we can observe three things here. The first thing is the beginning and conclusion, or the beginning and the end. Now has something called as CLS token and SCP special tokens. Now although these tokens vary from model to model, they all serve same purpose, that is to mark the beginning of a sentence by CLS and to mark end of a sequence, which is called as SCP. The second thing to observe here is that a characteristic of this particular checkpoint is that all the tokens are lowercase. Okay, so here hello is capital, like H is capital in hello, but here if we load this model, that is DistilBERT base uncased. So here uncased means convert all the tokens to lowercase. If we import this case, then the case will be preserved. Okay, and the third thing to note here is, now let's take a more sophisticated example. Hello, I am an example of text classification which includes tokenization. So I'm taking this more complex example to tell my third point. Okay, in this third point, we observe that this tokenization word is divided into token and this one IZATION. Okay, which makes sense because these terms are not frequently used. Any token with double hash prefix, this one double hash, should be merged with the preceding token when you convert the tokens back to a string, since it denotes the preceding string is not white space. So this IZATION has to be merged with tokenization if you want to get back the original text, this original text. Okay. Now how to do that I'll tell you. So let's take a variable regenerate text. Regenerate text is equal to tokenizer. This tokenizer dot convert tokens to string, and in this we will pass these tokens. Okay, and we will print regenerate text. Here we can see that the input is now regenerated. So here the tokenization and everything is now what we expected and what we provided as input. Okay, so this is how you can tokenize the data. You can get input IDs, you can get tokens, and you can regenerate the entire text. Now here a bonus thing I would like to tell you. So let's play with this tokenizer variable. This tokenizer. Okay, let's print the vocab size. So print tokenizer dot vocab underscore size. Again, yeah. So this tokenizer dot vocab size is 30,522. So DistilBERT has this many tokens. Okay, now if we want the maximum length of tokenizer, so tokenizer dot model max length. The maximum length is 512. So each token is represented by a vector of 512. Then we can also print tokenizer dot model input names. So here tokenizer dot model input names is input IDs and attention mask. Now let's tokenize the entire data. So now we have seen the tokenization for a sample of text. Now let's tokenize the entire data. Okay. So we will define a function. So this tokenize whole dataset, and let's take an input batch of sentences. In this, let's take a tokenized batch variable. We will call the tokenizer. Okay, and then we take this input batch of text, because we need to tokenize this text and convert it into a list, and we set the padding to be true and truncation equal to 2. So it will truncate to its maximum length. Okay, and we will return truncation equal to true. Okay, and then we will return this tokenized batch, right? Okay. Now let's take a variable that is emotions encoded. Emotions encoded equal to emotions. We will use the map functionality, and we will call this function the entire function. Let's call this batch equal to true, and just this simple batch equal to true, simple. Let's run this. Okay, now it is tokenizing the entire data. So this first is it tokenized the training data, then validation data, and then the test data. Okay. So yeah, hooray! We successfully completed till tokenization. Now let's meet you in the next part for actually training the model, and we will see what all different techniques are there for training the model or training this text classification model using transformers. Thank you guys.